Good morning, everyone. Today we're going to continue our discussion of security protocols that we began yesterday. We'll talk about transport layer security or SSL. We'll have a demo on SSL, and then we will also talk about Needham-Schroeder and Kerberos. So before that, let's just summarize what we had done before. So we looked at basic authentication. Different kinds of variations. First and foremost, there is one way where one party authenticates himself or itself to the other party, but not necessarily the other way. And then you've got two-way or mutual authentication. In addition to that, you could have authentication on the assumption that there are long-term secrets. Shared between the two parties. The other assumption is one or more parties has a digital certificate. So we took various combinations, one way with a long-term secret, one way with a certificate, mutual authentication with long-term secrets, and then mutual authentication assuming a digital certificate, or both sides perhaps having digital certificates. Then we looked at the next thing, the next enhancement to this, which is entity authentication. So all of this is entity authentication as opposed to message authentication. We then looked at entity authentication in conjunction with session key agreement. And then finally, we looked at the use of nonces or timestamps or both. So those are very basic authentication protocols that we considered, but they are the building blocks of various widely used protocols today. And some examples of these would be, so this is the protocol for use on the web, SSL. This is at the transport layer. Then we have IPsec, which is at the network layer. Then we've got various wireless protocols for wireless LANs. For example, WEP, WPA, 802.11i actually, and then other wireless protocols for cell phones, for example the 2G, 3G, 4G, etc. So all of these have the building blocks of all of these protocols are indeed what we considered yesterday. We will now move on to take the first of these, which is SSL, Secure Socket Layer. So another name for SSL is Transport Layer Security, TLS. History. SSL has emerged as the principal means of securing communications between an internet client such as a browser and a server. So its roots go back to the mid-1990s by a company called Netscape, which was in the browser business. It was standardized by IETF in 1999 and was called TLS, or Transport Layer Security. Today these two acronyms are used interchangeably, Secure Socket Layer and Transport Layer Security. So where does SSL sit on the network stack? SSL is typically sandwiched between TCP, so it only runs over TCP, and some application layer protocols such as HTTP, FTP, SMTP, IMAP, etc. Typically when SSL is used, the application protocol is suffixed with an S. So for example, HTTPS as opposed to just HTTP. So here in a picture, this is the application layer, this is the transport layer, and between the two sits this SSL, and the SSL protocol itself has got two parts. The most important one, the SSL handshake protocol, and then the other important one, the SSL record layer protocol. In addition, the SSL handshake protocol, you have another protocol that acts as the, when you move from SSL handshake to SSL record layer protocol, you typically go through this change cipher spec protocol, which is actually one of the messages, as we will soon see. So once again, the two layers, the handshake protocol and the record layer protocol. So we are going to discuss in detail what is this handshake layer protocol, all the different messages. And then when you come to the lab in the afternoon, you will actually use Wireshark to inspect all those messages, to inspect the digital certificate, etc., etc. So what does SSL provide? So we saw different things yesterday, like authentication, integrity, confidentiality, non-repudiation, etc., etc. So which of the following is provided by SSL? So server authentication, this is absolutely mandatory for SSL. Then client authentication, this is an option, so you don't necessarily have to have that. So visualize internet banking, you've got the customer and then you've got the bank. So typically what happens, as part of the record layer, as part of the handshake protocol, the bank authenticates itself to the customer, and the customer authenticates itself to the bank. It has to, of course. So the customer authenticates itself to the bank in the record layer protocol. So this is actually optional in the handshake protocol, but of course it is mandatory overall. So this is actually done very often by the use of passwords after the secure tunnel has been created by the SSL handshake protocol. Then there is message authentication. As we know, these are very important, entity authentication. So this is actually entity authentication. Now we've got message authentication, where you take every single message and you protect it. Both, you must be sure who the message is coming from, and you should be sure that the message has not been tampered with en route to the destination. So this is entity authentication, and this is message authentication, and then this is integrity checking. Message confidentiality, it's not the case that all the time you require confidentiality, so an option is provided. Don't forget, confidentiality takes place through cryptography, and that can be expensive, so there are times where you may not need it, and in that case it is shut off. And then finally, non-repudiation. So if both sides had digital certificates, then you could have non-repudiation, but typically it is the case that the server has a certificate, but most clients do not. So because a client does not have a digital certificate, it's more or less difficult or impossible to actually guarantee non-repudiation. So what are the main things that happen as part of the SSL handshake? The first thing is the agreement on a common cipher suite. So what does the cipher suite actually encompass? It includes all the algorithms that you use. So think of all the things that you might want to do. You might want to agree on common keys. So which key exchange method should I use? Yesterday we had seen Diffie-Hellman key exchange. Should I use Diffie-Hellman based key exchange, or RSA based key exchange, or something else? We need to compute integrity checks. Those are typically done through the use of a keyed hash. Which hash function do you use? MD5, SHA-1, etc. I would typically, if I need confidentiality, I would need to encrypt messages as they go from one party to the other. Would I use DES? Would I use AES? Would I use triple DES? Would I use RC4, etc.? All of those things have to be negotiated as part of the SSL handshake protocol, and all of those get included in what I call the cipher suite. So both sides negotiate and agree upon a common cipher suite. The next important thing that needs to be done is the server side has to send its certificate to the client, and that certificate should be validated by the client. So you have to check whether the certificate actually pertains to that server. You have to check the validity period. You have to check the signature on the certificate, etc., etc. So all of that thing needs to be done. The next thing is, how do you actually agree on common keys? So SSL has a very nice idea of a pre-master secret. So typically the pre-master secret is determined by the client and then encrypted and sent off to the server side. Encrypted with what? encrypted with the server's public key. And the server's public key is contained in the certificates sent by the server. So the server decrypts this message and retrieves the pre-master secret from that message. And then finally, integrity verification of all the handshake messages. How can I be sure that each of those handshake messages, so typically, except for this thing, all the other handshake messages are sent in the clear. How could I guarantee the integrity of each of those messages? And finally, and one of the most important, is how am I absolutely sure that the other end is the server I intend to talk to and not somebody posing as that server. So just because from the other end I get a certificate which has the server's name on it doesn't at all mean that I'm really talking to the authentic server, because that server certificate is all over the place and anybody could use it and send it to you and you would think it's the bank that you want to talk to. So clearly that's not enough just producing the certificate in this message. You need to actually prove that you are the owner of that certificate. You are indeed the principal whose name is mentioned in that certificate. So these are the messages, and as I said again, you will be in the lab today. We also have a demo of all this. You'll be in the lab and you'll actually see all these messages using Wireshark. You'll see the content of each of those messages and all of this will come alive. What is inside the client hello message, the server hello message, the server certificate, etc. So this is the client key exchange. I mentioned the pre-master secret. So that pre-master secret is encrypted with the server's public key, which is contained in the server certificate, and that encrypted pre-master secret is sent to the server, which is decrypted on the server side, and from that pre-master secret you derive master secrets and 6 other secrets that I'm going to mention a little later. The chain cipher spec message goes between, actually transits between this protocol. We talked about the handshake protocol and the chain cipher spec protocol. So this message actually provides the transition between the two protocols before we start moving to the record layer protocol. So once the handshake protocol is completed and this chain cipher spec message and the finished message, then we move to the next protocol, which is the SSL record layer protocol. So this is purely for entity authentication and for key exchange. Once we've agreed upon the keys, then we go on into the record layer part of this thing, where we will start exchanging messages which will also have integrity checks on them, so a MAC kind of thing, and if necessary they'll also be encrypted. But with which session key will they be encrypted, which key will you use for the keyed hash, all of that is determined in these steps. So we talked about these messages. Let's look at it once again. What is the sequence of messages? There's a client hello, and then there's a server hello and a server certificate. So let's focus on these two messages. What could be inside these messages? The information exchanged in the hello messages, the algorithm to be used in computing the MAC. So this is what I need to state. When I say I mean the client. The client or the client's browser, the user's browser, needs to state what is the algorithm to be used for computing the MAC. For example, MD5 and SHA-1 are two options. There are many others, like for example SHA-256 if you want higher security. Whether or not message confidentiality is required, and if so, which of these algorithms, say DES, triple DES, AES, RC4, etc. And then if you're using say AES, there are different key lengths. So which key length do you insist on? Then the key exchange method for communicating the pre-master secret. So there's Diffie-Hellman key exchange. You can do key exchange by simply using RSA and so on. So which method do you want to use? And if you're using Diffie-Hellman key exchange, then which group are you using? There are several groups for this, including elliptic curve groups, that is points on the elliptic curve. So which of these groups do you want to use? You meaning the client, and which of these groups is recommended by the server. So they both will present their own options and finally agree on one set of each of these things. And another important thing, don't forget, is these 32-byte nonces, which you will be seeing in the demo. So actually it's a 28-byte nonce and there is a timestamp. So the entire thing is about 32 bytes. So there is a nonce that is provided by the client, which is nonce RA, and then there is another nonce chosen by the server, which is RB. Now what is the purpose of these nonces, you might want to think about. What could these nonces be used for? A very interesting idea. So it turns out that this pre-master secret is chosen once, and then as a function of the pre-master secret you compute the master secret. The master secret is a function of that pre-master secret and of these two nonces. So if I keep the pre-master secret fixed for the duration of the session, I can keep changing these nonces from time to time so that I get a new set of keys and make the job of the hacker more difficult. It is a good idea to refresh these session keys within a certain interval of time rather than keeping that same key for the complete duration of the session, which might be several minutes, for example. I'd like to change it every few seconds. I don't want to incur a big overhead when I change the master secret. Now it turns out that this exchange of the pre-master secret is actually a time-consuming operation, as we will soon see. So if I keep that fixed, but if I vary the two nonces, then I can derive a new master secret a lot more efficiently. Okay, so we talked about the first two messages, which were the client hello and the server hello. The third message is the server certificate. So the server communicates its certificate to the client. On receive of the certificate, the obvious things are done. The client checks the owner's name, credentials, the URL, etc. for example, the validity period, the signature of the CA on the certificate. So if this is a certificate that you're doing internet banking with the State Bank of India, you will check and see who is the CA that has actually signed SBI's certificate, and you will verify the signature of the CA. When I say you will do it, it means your browser will do it. Okay, the next thing is client key exchange. So let's get back to that picture so that we can recall where this is. Client hello, server certificate. Once again, what is in this message? A cipher suite, which algorithms I'm willing to support. There's also a session ID inside this, and there is a nonce from the client side, and in this there is a nonce from the server side, and again a statement of which crypto suite I'm willing to support. And then there's a server certificate. Now we go to this client key exchange. So this is the pre-master secret I was talking about, and you can actually you can't actually see this in Wireshark because it's going to be encrypted, but it's a 48-byte random number. So the client chooses a pre-master secret, a 48-byte random number. This is encrypted with the server's public key. Notice that the public key was obtained in the server certificate and sent. So the pre-master secret is encrypted with the server's public key, which is contained in the server's certificate, which was sent to the client, and this encrypted thing is sent to the server in the client key exchange message. The server uses its public key to decrypt the encrypted pre-master secret. So this is a misprint over here. It should be the private key. So the server uses its private key corresponding to the public key in the certificate to decrypt the encrypted pre-master secret. Now, one way of doing this is to use simply RSA. So I use RSA and the server's public key to encrypt the message, and here the server uses its private key to decrypt the message. So this is a misprint. It should be private key. Now, as you might be aware, in RSA, the private key operation is much more time consuming compared to the public key operation, and both of them are much more time consuming compared to a secret key operation using secret key cryptography. So RSA is more time consuming, much more time consuming compared to, for example, AES or DES. So this becomes a critical step, this decryption step, because it takes a long time. So that's why I mentioned before that a good idea is to have the pre-master secret sent just once. From this you derive the keys based on the nonces and so on, and then you change the nonces after a few seconds, for example, and then rederive the master secret, keeping the pre-master secret fixed. So here's the actual expression without getting into unnecessary details. Both the client and the server compute the master secret from this expression. So what is this function? This is a so-called pseudo-random function, basically like a cryptographic hash, which takes as inputs the following. So the master secret is a function of the pre-master secret. It's a one-way function like a cryptographic hash of the pre-master secret and the nonces that were chosen by the client and the server, and then some predetermined constants. So from that I compute the master secret. So I can get a new master secret if I keep this thing fixed and just vary these two things. I would like to keep this thing fixed because communicating this and decrypting this and so on takes a lot of time. So from time to time, I will change the master secret. How? Only by changing these two values, even though this thing is fixed. And why do I want this thing fixed? Because it incurs a lot of overhead. So here f is an hmax style function, while the constants are predetermined values known to both client and server. Okay, the derived secrets. So now once again, from the master secret, from the pre-master secret, I derive the master secret. And from the master secret, I'm going to derive 6 different secrets that both sides will actually derive them. So these are secrets known to both sides, the browser and the server. So what are these secrets? The initialization vector for encrypting messages from the client to the server. So as we have seen before in the case of say CBC, that is DES in CBC mode, you require an initialization vector to start the entire thing. So these initialization vectors will be derived from the master secret. Then the secret itself for encrypting messages from the client to the server, and another one from the server to the client. So the key that is used for messages from client to server is different from the key that is used from server to the client. And once again, the initialization vector for encrypting stuff that goes from the client to the server, that's one initialization vector, that's this, and then from the server to the client, that's the other one. And then finally, don't forget, one of the most important things is to integrity protect every message, and we do that using the MAC. Another term for that is the keyed hash. So because it's a keyed hash, you need a key. So secret for computing the keyed hash or the MAC on messages from the client to the server. So the server MAC secret and a client MAC secret. So both sides should know all these 6 secrets to be able to encrypt and decrypt, or to be able to integrity protect and to verify the MAC. So I mentioned before, in the transition between the SSL handshake and the SSL record protocol, there is another protocol that you momentarily go through, and that is the chain cipher spec protocol, which is triggered by this chain cipher spec message. So both parties create and transmit a chain cipher spec message. This message signals a transition that from now on the cipher suite just negotiated and the keys just computed will be used. And then there's a finished message. So let's just go back to that picture just to make sure we understand where these things fall in place. Client hello, server certificate, communication of the pre-master secret, and now this chain cipher spec message, which basically signals that from now on we'll start using the keys that we have just derived. And let us see these two important messages, the finished message. So let me just say before that this finished message is going to contain a MAC computed in all these protocols. Now the thing is, all of these messages except for this one, all of these messages are in the clear. So what prevents a hacker from coming in the middle over here, a man in the middle attack, and changing certain things? So to prevent that from happening, what you do is you integrity protect them, so that even if somebody tampers with them, you can detect the tampering. So that's why you will compute in this finished message, you will compute a MAC from this end and send it across, and the same thing will be done in this finished message. He will take all these messages, string them together, and compute a keyed hash or a MAC on all those messages, and send the MAC in this finished message. So this guy, the client, is sure that he's talking to the right server. So this is the important component in the finished messages. So both sides communicate a finished message to the other. The finished message includes a keyed hash on the concatenation of all the handshake messages sent in the preceding steps together with a predefined constant. The keyed hash serves as an integrity check on all the previous messages. So there are two aspects of this, the integrity checking and just as important, the authentication, especially the authentication of the server to the client. The client to the server authentication takes place through the password as part of the SSL record layer protocol. So the handshake basically creates a secure tunnel, and across that tunnel the client sends its password. So how is actually server authentication? How can I be sure if I am the client, how can I be sure I'm talking to the right server? So at what point precisely does the client authenticate the server? As I mentioned before, it is incorrect to say that just because I received a certificate from somebody, I conclude that that guy that I received the certificate from is the actual principal on that certificate. For example, take a particular bank, say HDFC Bank. So many people receive HDFC Bank certificates. So you can just take that certificate and send it, somebody can take that certificate and send it to you. Just because you have received that certificate from that person doesn't mean that person is HDFC Bank. So it's much more than that. Server authentication is much more than just receiving the certificate from the server. So when does the actual server, when can I, the client, be sure that I'm talking to the right server? So here is the logical steps. The key used in the keyed hash contained in the finished message is one of the 6 derived keys. So I mentioned before there are 6 derived keys, including one of the keys is, 2 of the keys are to compute the keyed hash, one for client to server communication and the other for server to client communication. So the key used in this is one of the 6 derived keys. So unless I know those keys, I can't compute this. And to know those keys, where did I get those keys from? The server computes the key from the master secret. So unless I know the master secret, I can't compute those 6 keys. Unless I compute the 6 keys, I can't correctly obtain this keyed hash. And to obtain the master secret, how did I obtain that? The encrypted pre-master secret could only be decrypted using the server's private key. So unless I could decrypt that key message, you remember the message over there after the server certificate, unless the server could decrypt that message, he could not obtain the pre-master secret. So the only way he can decrypt it is by being in possession of his private key. So if he has the private key, he can decrypt the message and obtain the pre-master secret. If he obtains the pre-master secret, he can derive the master secret. How? Because this thing is a pseudo-random function of the pre-master secret and the 2 nonces. And once you obtain this, once again using a pseudo-random function, you can obtain all those 6 secrets. And one of those secrets is used to compute this keyed hash. So once the client gets the correct keyed hash and verifies it, then and only then he concludes that he's talking to the right and authentic server. So by verifying the keyed hash from the server, the client is convinced of the authenticity of the server. Okay, so now we talked about sending this pre-master secret, and there are a rich number of ways in which you can actually exchange the key. So as mentioned before, the client chooses the pre-master secret and encrypts it with the server's public key obtained from the server's certificate. It is possible that the server's certificate may be used exclusively for signing. So as I mentioned yesterday, there are some certificates that should be used only for signing, that is the corresponding private key corresponding to the public key in that certificate should be used exclusively for signing and nothing else. So in that case, what should I do? The server has a certificate, but that is a signing only certificate. So in that case, what he can do is, the server may generate a public key private key pair, an ephemeral public key private key pair, and then sign this saying that it is I who came up with this pair. I sign it with the public key contained in my signing only certificate. So I sign it with the private key corresponding to the public key in my signing only certificate. That is what I will send across. So the server may generate a public key private key pair, sign the public key parameters and send the public key to the client with this signature only certificate. So there are so many different options, and of course don't forget that you can use multiple Diffie-Hellman options as well. You could have a certificate with the Diffie-Hellman parameters in them and so on. So we had seen this yesterday. The server may instead communicate a Diffie-Hellman certificate which includes a signed copy of GP and G raised to A mod P signed by the CA. GP and G raised to A mod P, this is the public key. The client chooses a random integer B, computes G raised to B mod P and sends this to the server. The client computes then G raised to A mod P to the power of his secret B over here. And this G raised to A mod P came from the server certificate. So he takes the public key of the server and raises it to the power of his secret, and the server takes the G raised to B, the partial key which is sent by the client, and raises it to the power of A, which is his secret. So the server's secret is little a, or the server's private key is little a, and the corresponding public key of the server is G raised to A mod P, which is contained in the certificate together with the Diffie-Hellman parameters. So both sides agree on a common pre-master secret, G raised to AB mod P. There is also another nice idea in the context of SSL, and that is the idea of a session and a connection, which is basically what I tried to explain before. So it is good security practice to change keys during a long-lasting session. So you refresh these keys. Don't keep the same key for, say, several minutes. Try to refresh it, even though the session might take several minutes, but you refresh it. Now SSL has provision for changing the keys by creating new connections within an existing session. So far, the largest component of the overhead in creating a new session key is the RSA private key operation. Basically, RSA decryption of the pre-master secret at the server side. So can I somehow obviate the need for this? This overhead is obviated by creating a new connection within an existing session. The new master secret will be, as we know, the master secret is a function of the pre-master secret and the two nonces. The pre-master secret remain the same. By keeping it the same, I guaranteed that the server wouldn't have to go through the headache of doing another decryption which takes so much time. So I keep the pre-master secret the same, but I change the nonces. So I have a client hello and a server hello to change the nonces, because the client hello, the server hello contains those two nonces RA and RB, and those are used together with the pre-master secret to obtain the master secret. So thereby I have changed the 6 keys by only changing the master secret and not the pre-master secret, because the master secret is a function of the pre-master secret and the two nonces. So once again, this thing is summarized over here. In creating a new connection, the pre-master secret, which is part of the existing session state, is not chosen anew, because that would incur an overhead. Instead, a new master secret is computed as a function of the existing pre-master secret and 2 fresh nonces contributed by client and server. So it is very good security practice, as we saw yesterday, for both sides to contribute towards creating the session key. So we used SA and SB in the protocols yesterday. So here also, both sides contribute RA and RB towards the master secret. And finally, the SSL record layer protocol. So this is the handshake and all the trouble we had to go through to obtain those 6 keys, and also do entity authentication, in particular authentication of the server. Now once we are through with all that, we can simply go ahead and integrity protect every single message, and if necessary, encrypt every single message. So that is done as part of the SSL record layer protocol. I already have the keys. Now I can just go ahead and compute the MAC for each message, and optionally also encrypt it. So the SSL record layer protocol is used to securely transmit data using the negotiated cipher suite. So we've just done that in the handshake protocol, and we've also derived the keys as part of the handshake. Now we go to the record layer protocol, whose main tasks are computation of a per message MAC and encryption. So this is a distinction between entity authentication and message authentication. Entity authentication took place in the, at least server authentication took place in the handshake, and per message authentication and integrity protection takes place as part of the SSL record layer protocol, using the keys that were computed and derived in the handshake. In addition, if the data to be transmitted is very large, it performs fragmentation. Each fragment is 16 kilobytes or less. So it's the duty of this guy to do the fragmentation, besides the all important duties of protecting every message in transit. By protecting, I mean integrity protecting, guaranteeing the integrity of it against tampering and so on, and also encrypting if indeed that is necessary. So with that brief introduction to SSL, let us now move on to complete this discussion of security protocols. We will now look at a different kind of protocol which uses what's called a KDC, or Key Distribution Center. So prerequisites for authentication: between two parties, we have assumed that both sides share a secret or that one or both sides has a public key, private key pair. Let's get back to SSL and see what were the assumptions made over there. The fundamental assumption is that the server has a certificate, but the client does not. So either there is a long-term secret that both share, or there is a certificate. So in the case of internet banking, the server has a certificate and the client, the user, has a long-term password that he shares with the server. So in the former, when you talk about using certificates or you talk about secret keys, key management is a problem. We've seen this before. In secret key cryptography, key management is a problem. And in the case of public key cryptography, certificate-based authentication, etc., performance is a problem because RSA operations are very expensive. So is there some sort of an alternative approach which handles both? And here we come to the role of the KDC. So a third approach is to employ a trusted third party which functions as a key distribution center. So what is this KDC? Each user registers with a KDC and chooses a password. So we assume, for example, a campus where you've got multiple users, and each of those users, to use the facilities, has to enroll with this KDC. The user has to choose a password, which is basically a long-term secret, and the key is a function of the password. So some sort of PRF, pseudo-random function of the password, and maybe some predetermined constants, and that is exclusively shared by the user and the KDC. So basically, the user has the password, and then the system, the password software, will actually convert the password into a key, and that key will be used to, for example, authenticate the user to the KDC. So the main function of the KDC is to securely communicate a fresh common session key to the two parties who wish to communicate with each other. So let us see how actually that works. So the main function of the KDC is to authenticate the user and basically communicate in a secure fashion a common session key to the two users so that they can communicate securely for the duration of the session. So this is the key distribution center. These are the two parties. So let's see how the communication might, what the communication might be. So A says, I am A and I wish to communicate with party B. And then what the KDC does is it actually sends a session key to A encrypted with A's the long-term key that A shares with the KDC. So that A over here means encryption using a function of A's password. So both A and KDC can decrypt it. So KDC has encrypted a message and A can decrypt the message, and nobody else can read that message or understand it because it requires knowledge of A's password. In the same way, KDC also sends the same session key encrypted with B's password to B, so only B can read it. So now both A and B have access to this KAB, the session key, and they can communicate with each other securely using that session key for the duration of the session. So the KDC chooses a fresh session key KAB, which is this thing. It sends this key to A after encrypting it with A's long-term key KA. Likewise, it sends this key to B after encrypting it with B's long-term key KB. Now there are several problems with this approach which you will find. For example, one of the important things is the lack of synchronization. This guy might receive the key, this guy might receive it after a long delay, etc., etc. And there are many other attacks that are possible, like the man-in-the-middle attack and replay attacks, etc. So let us try to improve on this and see whether an improved version of this thing is vulnerable or not to other kinds of attacks. So an attempt to do this was by Needham-Schroeder. It's called the Needham-Schroeder protocol. So here's what it looks like. So here is the party A that wants to initiate communication. Here is B, so A wants to talk to B, and here is the KDC. So the first message is between A and the KDC. Hi, I am A and I would like to talk to B. So basically, provide both of us a session key. That's basically what he's saying. Authenticate me and provide a session key to both of us, and so that nobody else has that session key. So what does this guy do? He creates what's called a ticket. So this ticket contains, so this ticket is going to be, so this is the important thing, the ticket that is eventually going to be given to B. So you will see that this is received by A and forwarded by A to B. So what does this ticket contain? As you might expect, it will contain the session key, it will contain the identity of the other party. So basically this guy is telling this guy that I'm enclosing here with this ticket a session key for the duration of the session with party A. And so that nobody else can read it, I am encrypting it with the long-term key that you, Mr. B, shares with me. So this is the ticket. And together with the ticket, of course, he also encloses the session key as another part of this message and encrypts the entire thing with A's long-term key so that only A can read it. So when this message goes to A decrypts it, he gets this session key, and then he gets this thing. Of course, he cannot see what's inside this because it's encrypted with B's long-term key. So he receives this entire thing, and then he sends that ticket. Basically, just this thing is simply forwarded after being decrypted, and then he sends a nonce, which is R1 in this case. So basically, he's telling him, here is my challenge to you. If you are really this guy, then decrypt it using the fresh session key and decrement it by 1 and send it back to me after re-encrypt it. So basically, what will B do? There are two parts of this message, this thing and this thing. So B will take this. B has his own long-term key. So with his long-term key, he will decrypt this. He will realize that A wants to talk to him and that A has already communicated with the KDC. This ticket has come from the KDC. He will pull out the session key. Now, with knowledge of the session key, he will be able to decrypt this nonce. This AB over here means that this message is encrypted. This nonce has been encrypted by A with the common session key. So if he is really the good guy, he will be able to decrypt this. He will be able to retrieve this session key, and with the session key, he'll be able to retrieve this nonce. So once he does all that work, he will then create a message which contains that nonce decremented by 1 and a fresh nonce which serves as a challenge to A. So basically B is saying, I have responded to your challenge. I've been able to obtain R1 because I'm the right guy. I'm decrementing it and sending it back to you for verification, and I'm also enclosing a nonce which is my challenge to you, this R2. So he sends this thing, and then in response what she will do is she will decrypt this thing because she has the session key. She'll retrieve the R1 minus 1, verify that this is a decremented version of the nonce that she chose, and then she will take the nonce that he chose, decremented by 1, and send it to her, encrypted with this, so that then he will realize that she is the authentic A. So this is the first version of the protocol. So the intention is not really to look at every single attack on this protocol because that would take a long time. It's just to show you that even though this protocol looks correct and okay, there actually are bugs in it. And it's not very easy to always detect the bugs. So let us see one possible bug, some sort of a man-in-the-middle attack, for example. So this is basically just an explanation in words of what was going on over there. So the question that's floating in our minds is, how can we actually attack this protocol? It looks pretty sound. So once again, this is what it looks like. I am A, I want to talk to B. Give me a session key for myself and for the other party. So this guy retrieves A's long-term secret from his database and B's long-term secret, that is basically their passwords, function of their passwords. And from that, he creates this message. First and foremost, he creates a ticket to be given to B. So he generates a session key, KAB, creates a ticket to be given to B, which contains the identity of A and the session key, encrypted with B's long-term secret, and puts that stuff together with the session key in a bigger message, which is encrypted using A's long-term secret. Sends it to A. A starts to decrypt this entire thing. He retrieves the session key, and then he retrieves this token. He cannot make any sense of this token because it's encrypted using B's long-term secret. So what have we accomplished over here? A has now received the session key because he can decrypt this message. The A over here means encrypted using A's long-term secret or password that he shares with the KDC. The AB means a session key to be shared only for the duration of the session between A and B. So then what A does, after he's retrieved this thing, he just simply forwards that stuff. And then he now says he wants to challenge B. Both have to challenge each other. So he challenges B and says, here, I am generating a fresh nonce. The word fresh is very important so that there's no replay. I'm generating a fresh nonce R1 and I'm encrypting it with the session key. I'm sending it to you. If you really are B, what can you do? What are the things you are supposed to be able to do? If you really are B, you are supposed to be able to decrypt this ticket and obtain the session key. Because I understand that KDC has encrypted the ticket with the long-term secret that you share with the KDC. So if you really are the right guy, decrypt this and obtain KAB. Once you have obtained KAB, read what is my nonce, obtain my nonce, decrement it by 1 and re-encrypt it and send it to me so that I can be sure you're really the right guy. So what he does, he decrypts this, he gets the session key, he decrypts this thing with the session key that he's just retrieved, and then from that he retrieves this R1 challenge. He takes R1, decrements it by 1, and then adds his own challenge to A, which is R2, and says, now I challenge you. If you are the right person, you should be also able to use the same session key that was given to both of us. Use that session key, decrypt this, and obtain these two things. The first thing is a verification, so a response. So the first thing he does is he sees what is inside this. After decrypting it, is this really the challenge -1? Then I'm convinced that this is indeed B. And then I will issue my own, I will respond to the challenge from B. So I will take the challenge R2, decrement it by 1, and then encrypt it using the session key and send it to B. And then B will decrypt this and verify whether what's inside over here is the nonce that he chose -1. So again, this is a fresh nonce. If everything works out, then it appears that they will be sure there's no replay, etc. And this KAB is a fresh key that was given by the KDC. Unfortunately, many of these protocols are very treacherous and there could be bugs in them. So let's see what is the bug in this protocol. So here is a standard man-in-the-middle. We've already encountered a man-in-the-middle attack in connection with the Diffie-Hellman key exchange yesterday. Now here's another version of this thing. So A sends the first message, I am A, I want to talk to B. And there is an attacker who now stands in the middle, intercepts this message and changes it, changes the B to an X. So basically he's telling the KDC, I am A, impersonating A, and I want to talk to X. Who is X? X is himself. And the KDC receives this message, so he can choose a different, go to a different machine or something like that. So KDC doesn't realize that X is saying that he is A and that he wants to talk to X. KDC is not able to figure out that he has spoofed this message. Basically, the KDC only goes by things like keys. So he accepts it that I'm receiving a message from A and that A is saying he wants to talk to X. So what does he do? He prepares a very similar kind of message. He will encrypt, he will create a token or a ticket which contains the session key and the identity of A, because A wants to communicate. So A is the initiator, initiator's ID over here, the session key, and he'll encrypt the ticket with X's long-term key. So this is X over here and sends it across to A. But before that, he also encloses the session key, and the two things together, this pair of things, is encrypted with A's long-term key that is shared with the KDC. So A is able to retrieve it. A and only A can decrypt this message and obtain this thing. So what's the next thing that happens? So now A sends forwards this thing to supposedly B. So A is thinking that he's actually talking to B. X stands in the way, intercepts the entire thing, and guess what? KDC was made to believe that A wanted to talk to X. So therefore he encrypted this ticket with X's long-term key. So X is very happy. He stands in the middle He takes this message, and because it's encrypted with X's long-term key, he can very happily decrypt that message and retrieve the session key. So he retrieves the session key and then chooses a nonce, encrypts it with the session key, and says, I challenge you to decrypt it, and so on and so forth. So the rest of the protocol is as before. And so she's able to decrypt it, and then she responds to his nonce, which is R2, in this message. So why is A convinced that she is talking to B? Because A issued a challenge over here, which is R1, and X successfully responded to that challenge R1. So therefore X is convinced that she's talking to B when she's actually talking to X. So the standard man-in-the-middle attack. And now all the communication will go on between them, and X will know everything that she wants to send to supposedly B. So to get rid of this problem, and there are actually several problems, several kinds of attacks, so look at the text for more of these attacks. And this is the final version actually. There might be some typos in this. Please bring it to my notice if you see any typos. So it's a slightly larger protocol with more messages. So it's interesting to see what is happening over here. So now A actually initiates the communication to B, saying, I'm A, just by the way, just to inform you that I'm going to start, I would like to talk to you. If he also wants to talk to her, then he will send a message. Now, a very interesting message. In the interest of preventing replay attacks, I want to generate fresh nonces. So I generate a nonce which is R4. I can't see this very well, but I think it is R4 out there. So a nonce R4, and then I encrypt it with my long-term secret that I share with the KDC. So I send this message across to A, and A simply forwards this. So basically what he's saying is the ticket that the KDC sends me should also have this R4 inside it. Then I will know for sure that it has come from the KDC. So he encrypts this because only the KDC can decrypt this message and retrieve the R4. I'm not able to see those numbers very well. Okay, great. Yes. So this is A and B, and this is R4. So this guy B, he puts R4 out there, encrypted with the long-term secret that he shares with the KDC. So now this goes over there, and A sends a message to the KDC saying, I'm A, I want to talk to B. And by the way, just to make sure that this whole thing is fresh, whatever is your response, I'm also including a nonce that I just generated. And I'm enclosing an encrypted nonce that B just generated, so there is no confusion later on. So that nonce is R4 and encrypted with B's long-term secret, and my nonce is R3, sending it to the KDC. And then the KDC responds with this jumbo message, which must contain a ticket. So there is another brace over here that's not in this. So the ticket is encrypted with B's long-term secret as before. So this is a ticket to you, Mr. B. Since A wants to talk to you, I'm enclosing the identity of A. I'm enclosing the session key. And then just to convince you that this is not a replay kind of thing, you generated a nonce over here. I'm enclosing that nonce just to convince you. So this is the entire ticket now. You can open it and you can see what's inside this thing and verify that your nonce is over here. So this is one part of the message, and the rest is the session key KAB that A is able to decrypt, and the identity of B, and also this R3. So this R3 was sent over here. Now the KDC says, this way you will believe that I'm really the KDC, because I'm including this R3 which you sent in the clear. I'm including that nonce over here, and I'm encrypting it with a long-term secret that we share. So now you will be convinced, because only I, the KDC, can encrypt this R3. So you decrypt it and verify that you get back R3, the thing that you sent over here. And then the rest of the protocol is like what we've seen before, the mutual authentication. So this is hopefully the corrected version of the Needham-Schroeder protocol. Extra nonces and so on, but those are just to guarantee the freshness of these messages so that you are not vulnerable to a replay attack or a man-in-the-middle attack. Okay, so another protocol that is widely used and that has been inspired by Needham-Schroeder is the Kerberos protocol. So let's look at the wish list for Kerberos. First and foremost, you have something like a campus, a network with multiple users and multiple servers, in an organization such as a university campus. A user once logged in may wish to access, so I log in just once. I don't want to mess with this password thing again and again and again. So I log in just once with my password. I wish to access different resources such as an email server, file server, etc. in the course of that login session. One possibility is for the user to have multiple passwords on each of these servers, because I want to access each of these servers. So a separate password for each server, but that's a big hassle. However, having humans remember and update multiple passwords is not very practical. Now a user could use the same password for all the servers. So the same password for this server and so on, but distributing and maintaining a password file across multiple servers is a security hazard. So I don't want to do this either. So can I think of something smart? Then as far as the password is concerned, the password should not be transmitted in the clear because anybody can eavesdrop on it. It should not be possible to launch dictionary attacks using the eavesdropped upon messages containing a function of the password. So if I've got the hash of the password in the communication, if I get that, I can launch a dictionary attack and possibly get the password out. So many different considerations. The password itself should not be stored on the authentication server. Rather, it should be cryptographically transformed before being stored. It should not be possible to launch dictionary attacks by obtaining a file containing the cryptographically transformed password. So you can have dictionary attacks on the password file. You can have dictionary attacks on messages that contain the password or a function of the password. So we have to be careful about all of these things. So what is the final solution to this? Okay, besides that, there are just a little bit more. A user enters her password only once during login. So I mentioned this before. Thereafter, she should not have to re-enter her password again and again to access different servers. So this feature is commonly referred to as single sign-on. The other thing is when I enter my password, I don't want it to be there for the next half an hour because there could be attacks on the RAM and so on and so forth, all sorts of stealth attacks. So the password should reside on a machine for only a few milliseconds after it has been entered by the user. Thereafter, all vestiges of the password, even if I am logged in for the next 5 hours, that password or anything related to that password should not be there on that machine. So thereafter, all vestiges of the password should be destroyed. An image of the password should not linger on in either volatile or non-volatile memory of the machine. So one solution to this is Kerberos. Again, this has gone through many different versions. So this is a widely used protocol supported on several operating systems, including Vista and Microsoft Server 2008. The key distribution center that we talked about before is actually split logically now into two parts, logically not necessarily physically. It's split into two entities. The first entity is called the authentication server or AS and the ticket granting server TGS. So AS and TGS. Like before, the ticket is the mechanism used to safely distribute session keys. So I will authenticate myself to somebody, get a session key, and then use it for the duration of the session. So the same basic idea, but with a little bit more, some more frills. So some more details here. So there are two kinds of entities in the system. There are human beings who are users, and there are servers who provide service. So each human user A of the system shares a secret KA, a long-term secret, which is typically a function of the password, with the authentication server. So once again, the KDC, key distribution center, has been logically split, so different functions for the AS and the TGS. So the KDC is now split between the authentication server and the ticket granting server. And each human user shares a secret that is a function of the password with the authentication server. This secret is essentially the hash of the user's password. Then each server B shares a secret KB with the TGS, not now the AS, but the ticket granting server. Unlike the Needham-Schroeder protocol, Kerberos makes use of timestamps. So how this basically works is when you log in with your password, the AS is involved in authenticating a user when she attempts to log in to the system. The AS then issues a ticket granting ticket to the user. Just keep this safely. You've logged in. I'm giving you this one-time ticket. It's called a ticket granting ticket. Whenever you want a service granting ticket, you should produce the TGT. Produce to whom? to the TGS. So you've logged into me, your business is done. You log into me, I'll give you this TGT and don't bother me for the rest of this session. Now you start bothering the TGS every time you require different services. So for each different server that needs to be accessed, the client approaches the ticket granting server with the TGT that was obtained from the AS. The TGS first authenticates the user and then provides the user with a service granting ticket. So it authenticates, but without the use of the password. That's the beautiful part. So the TGS authenticates the user and then provides the user with a service granting ticket to be handed over to the server whose service is required. Now the details of the messages are in the text. In the interest of time, I'm not going to go through the detailed structure of each message, what it contains and all the crypto stuff. So you can see that for yourself. But basically these are the messages. There are a total of 6 messages. So the client over here, the KDC, which is logically split up into the authentication server and the ticket granting server, and then this is your server, which could be any generic server like a file server or a web server or whatever. So the first step, C requests a ticket granting ticket. So you produce your password, some function of the password is used to create a message, and then that thing is sent over here. It is verified and so on, and if it verifies successfully, then the AS produces a ticket granting ticket in this message and conveys it to the client. So that's message number 2. C receives a ticket granting ticket from the AS, the ticket granting ticket. Now the client continues its work. At some point in time, it needs the services of some server. So what does it do? It goes to the TGS for that purpose. So only a one-time involvement or interaction with the AS, and thereafter you might go again and again and again and again to this guy to request multiple services. So for the first service that you require, you go to this TGS, request the service granting ticket, you produce the ticket granting ticket to him. So you produce the TGT, the ticket granting ticket which was received in this message, and you request for a service granting ticket, SGT, and a session key. So you produce the TGT and request the service granting ticket SGT. You get the SGT together with a session key. And then it also produces a ticket which contains the session key for the server. So that is then sent to the server, and the standard mutual authentication between the client and the server, you require fewer messages because you're using timestamps rather than nonces. So this is basically how Kerberos works. Okay, so with that, more or less, the actual details of these messages I think you should go through because they're very instructive and very interesting to see exactly how authentication takes place. So the details of these messages are contained in the text and the chapter on Needham-Shoreham, and it's actually Security Protocols Part 2. Okay, so this will happen at the end of the next session.